WCOB with Mats.
All right, Jennifer, thank you very much. We have moved back inside for part 2 of our Wise Guy segment this morning. It is 7:25. Now, we moved inside. This is not dangerous. That's not why we had to move in, right, Matt?
As far as you know.
As far as you know. Matt Sellen, our U of I physics professor, is here, and we're talking more about this big particle accelerator in Geneva.
Right. This, the LHC, the Large Hadron Collider is called. And the reason I'm talking about it today is it's actually turning on today.
Okay.
They're going to put the first beams around in one of the circulating tunnels today, basically.
Okay. What time? Should we hunker down and be nervous about this?
No, they're not going to actually collide beams in it for another month or so. When they do collide the beams in it, the energy that will be produced will be about, well, between 5 and 7 times what they've ever done up at Fermilab, which is already a very big place.
Okay.
And so the idea is that they're really going to get into the very first microseconds after the Big Bang to try to really explore how the forces work in our universe. And there are 4 basic kinds of forces, or 4 basic forces that we're aware of.
Okay.
And one of the big challenges for physics is to explain how they fit together with each other.
Okay.
Okay, and it's a really big challenge because the forces are so different in strength. And the very weakest force that we know about is gravity.
Okay.
It turns out. And you may say, well, look, gravity's pretty strong.
Yeah,
you know,
like
it holds me right down to the ground. But the reason gravity seems like it's so strong is that the Earth is pulling on you, right? And the Earth is really big.
Sure.
Okay? So if you just measure the gravity between, you know, my coffee cup and your shirt, for example, it's not very strong. This cup doesn't go zonk and stick to your shirt, right? Yeah. So the gravity for that reason is actually a very, very weak force.
Got it.
In contrast to that, the electromagnetic force, this static electricity, is just, you know, many, many, many millions of orders of magnitude stronger than that, given the number of particles that are interacting. So, for example, I can do, you know, we can do a static electricity experiment. We're going to do that right now. And so I have here a little gadget. All it does is there's a little rubber band that spins around in here, and it puts some charges up on this thing. And we know that like sign charges repel, okay? So here I have a bunch of little cups, you know, pie dishes, things, and I'm going to turn this thing on. And if you just kind of watch, you can hear a little humming noise.
I do.
And what we should see here...
It's moving.
Well, it's supposed to be flying off of there. You know,
like that?
There we go.
That's a cool trick.
Okay, and see how they're all kind of, I mean, okay. So now, you may say, well, it was vibrating or there was a fan or something, but that's not what happened at all. A few charges, just not very many, were placed on these cups, okay? And these things then repelled each other because there was very, very few charges, and it didn't take very much to get these things to actually move, right? Okay. If you took one of these, and I took one of these, and we stood about this far apart, and suppose I took 1% of the electrons on this and put it on that, so now this one would be positive, that one would be negative, the force between these two things would equal the weight of Mount Everest.
Really?
Yes. Okay?
Wow.
And that's only taking 1% of the charge from one to the other. So the electromagnetic force is enormous compared to gravity, okay? And that's a very interesting and huge problem. And so one of the things that people have never managed to do is kind of combine gravity with the other forces. Okay. Now, inside the nucleus, there's also forces, okay? And if we have just a second, you know that inside what's in an atom, the nucleus of the atom is positive. There are protons in there.
Sure.
They're all positive. They're all very, very close together. Why don't they just fly apart? Because this force is so strong. There must be an even stronger force inside the nucleus. And that's called the, guess what? The strong nuclear force.
There you go.
Okay, so...
Bada bing.
Bada bing.
All right, we'll keep an eye on this, Matt, so maybe we'll talk about it a little more whenever they fire it up again.
Oh, yeah.
All right. Thank you. You want to see a replay of the segments, go to our website, IllinoisHomepage.net. Click on The Morning Show. Look under The Wise Guy. We'll continue more with the Live United campaign outside the studios when we come back. Stay tuned.